whom she knows quite well. Cynthia is on the board of the Geologists of Jackson Hole. She is the secretary and communications director. She's also famous for her Tuesday presentations, and she's just a very solid individual. Without further ado, Cynthia, would you please take it away?
Thank you, Brent. You're such a gentleman. So again, my name is Cynthia Blankenship, and I have the pleasure to introduce my husband, Dan Creighton, as the speaker tonight. But before I do that, let me say a huge welcome to everyone. And we're so glad you could join us via Zoom. And although we're remote this evening, as a reminder, the Geologists of Jackson Hole have a long-time partnership with the Teton County Library and the Library Foundation. Our programs are part of the Science and Nature Tuesday evening programs that usually take place in the library, and we're very much looking forward to returning to the library sometime soon after the pandemic has eased. Meanwhile, we would like to thank St. John's Church for hosting our live events in Hanson Hall in the interim. Not tonight, but the next talk will also be live, a simulcast from Hanson Hall. So before I introduce Dan, our next speaker, I'd like to tell you about the next program, which will be October 19th, titled Dinosaurs, Allosaurus Assemblage, Predator, Pitfall, or Coincidence. And it is presented by Angela Reddick of the Wyoming Dinosaur Center in Thermopolis. And again, this will be both live and via Zoom, live in Hanson Hall in Jackson. And I also should mention this will be our last program lecture of 2021. So the next Tuesday programming after this 2 weeks time will be in January. All right, so now for tonight's speaker, Dan Creighton. He will be talking about oil and gas operations and their potential impact on freshwater resources. Dan earned his MBA and MA, so his bachelor's and master's in geology from the University of New York at Buffalo. His master's thesis was a study of the Menon Buttes near Rexburg, Idaho, just over the pass. His work was part of a NASA program using field geology on the Snake River Plain and comparing it to satellite photos on Mars. The Mars Analog Project was supported with support for the Mars exploration plan the U.S. had in the 1980s. And in the summer of 1980, Dan camped out on and mapped the Menon Buttes. He also managed to find time to explore the beauty of the surrounding area. His time in Idaho and Wyoming was the link to wishing to make Jackson Hole his home. But then for the next 36 years, Dan worked as a petroleum geoscientist on projects in the US, China, Colombia, Angola, Mozambique, and the Côte d'Ivoire. His last 10 years were spent working unconventional oil and gas projects in Texas and Oklahoma. Finally, in 2016, Dan fulfilled his dream to move to Jackson Hole with his wife and 3 children. He continues to work part-time as an advisor to Burgundy Exploration, a private oil and gas company working the onshore north slope of Alaska. So one final reminder, if you have any questions, please send them via chat, the chat feature on Zoom, to John Heberger. Thank you very much. Dan, over to you.
Okay, thank you very much. I'm going to go ahead and share my screen. And we'll get started. Is everyone able to hear me? I hope. So by this title slide, it looks like we'll be talking about hydraulic fracturing more than anything else, but that's really just a factor in building an oil and gas well. So we will be talking about other items as well. So let's go to the next slide and I'll show you what our outline will be. So we will first cover, I've broken it out into 3 phases. First, there's a drilling phase for a well. Then there's the completion phase. Then there's a production phase. And then finally, after we've covered these topics, then we'll go and investigate the information that I have that's about the Pavilion Field issues that have come up. So let's start in with the drilling phase. Key items for drilling a well safely and environmentally correct is to have a good well casing design, which will prevent groundwater contamination and also commingling of other zones that are deeper than the groundwater. Another important factor is the drilling mud system that is designed to have efficient drilling operations, but also to make sure that we don't have surface contamination because of how we're running our mud system. Finally, after we've drilled the well, we have to dispose of the drilling related waste, which is primarily drilling mud and cuttings. So we'll discuss that. And then last of all, reclamation of the drill site after it is no longer needed. So here's a little schematic to show we have some freshwater zones, some saltwater zones, and a gas sand. We'll consider this the target of this particular well. So the first thing you do is you drill your surface casing hole. You run the casing into the hole to the bottom, and then you cement it. And when the cement is run, it needs to be pumped so that it goes down the pipe, up the annulus, around the pipe, and all the way to the surface. And that way you've got full protection of the freshwater aquifers. Then you drill the next section of the hole. This would be an intermediate casing hole. Run the pipe in the hole, cement it again. Now, a second casing needs to have the cement be pumped all the way up into the previous casing to have an intact seal to keep fluids from being able to run up vertically in the annulus. Ideally, that cement would go all the way to surface. But in the case that if you're not able to, at least it needs to get into the casing string that's above it. So let's drill now the production hole. We'll run the production liner or casing into the hole and cement it. Again, like I said before, this cement needs to at least go into the intermediate liner, but ideally it would go all the way to the surface. So what you have casing and cement form two barriers for entry of production from the inside of the pipe to the freshwater aquifers. If you have intermediate casing and cement all the way to the surface, now you actually have four barriers that are protecting the fresh water from the fluids that are being produced by the well in the production casing. If you get the production casing cement all the way to the surface, you actually have six barriers that are protecting the fresh water from the production that's within the pipe. The risks to having an adequately cased well is one, not having the casing deep, the surface casing deep enough for the fresh water protection. And then the other is not having the cement be well done and have gaps and places where the fluids can flow up and down the wellbore, the annulus. The annulus is the space between the casing and the hole that was drilled. Now let's move on to while we're drilling. This diagram is just a schematic of the different parts of a mud circulation system. The mud pit is kind of not named correctly these days. In the old days, we used to dig a pit and then the mud was mixed up in it and it was an earthen pit. Nowadays, we use steel containers to hold the drilling mud. We have a mud pump that draws the mud out of the mud pit, pumps it up to the top of the drill pipe, down the drill pipe, all the way down to the drill bit. Now here we have a drill bit. The mud comes out of the base of the out of the jets in the drill bit, washes cuttings outward towards the annulus and then flows up the annulus, which is the space between the drill pipe and the boundary of the well bore that was drilled. So this is a rock boundary right here. So the drilling mud does two things. It cools the drill bit and it carries the cuttings out of the well. So now we've got the mud traveling up the well annulus, goes into the mud return line, then goes on to what we call shale shaker, which is a series of screens that allow the mud to fall back into the mud pit, and the cuttings stay on the screens and roll down a ramp. And in this image, the cuttings are going into a reserve mud pit. They're stored there temporarily. There's another type of drilling mud system that's an improvement over what we just looked at, and it's called a closed loop mud system. So this big gray tank that runs from here all the way, the whole length of this photo pretty much, that's the mud pit or mud tank. And then in this case, there still are screens that separate out some of the cuttings, but there are also centrifuges that remove even more of the drilling mud fluid from the cuttings. Cuttings end up coming down this ramp and go into this steel tank here. So it's a much more contained system, and it is much more efficient and less likely to have any surface spills than using a reserve pit would. All right, so the next slide, here is a picture of an actual reserve pit. This is a pit that's dug out with bulldozers adjacent to where the drilling rig is going to be set. They put a liner in it to keep the mud from soaking down into the ground underneath the pit. The cuttings, these are the shale shaker ramps, and you can see a pile of cuttings at the base of the ramps, and the mud tanks are over here. The mud pit is generally built according to the depth of the well that you're going to be drilling. So you need a certain volume as backup mud, reserve mud. That's why it's called a reserve pit, in case we have lost circulation and we lose mud and need to replenish it quickly. This is a reserve mud. Next slide. So now, once you've drilled your well, you've got to rehab the well location. In the old days, this is kind of what was done. Often the drilling mud gets pumped out of the pit, but the cuttings are left in the pit. And then in the old days, we used to just bulldoze the dirt back over the cuttings and bury it in place. That's really bad practice. Nowadays, we don't do that, especially if you have a closed loop mud system. None of this sort of thing happens. Most reserve pit burials were done in the 1980s or earlier. So let's summarize the water resource risk from all these various stages of the drilling process. The well casing design is critical, and if it's well designed and well executed, we have good groundwater contamination protection. If any of the facets of that design are not executed well, then we have a risk at getting groundwater contamination. The reserve pits are point sources for soil contaminants because if the contaminants that are in there will just leach into the subsurface over time very slowly due to rain and or if irrigation is reestablished on some land that's been abandoned by oil and gas operations, you can get water leaching the contaminants from the pit down into the groundwater. And then for all of the operations that we're going to be talking about, equipment leaks, pipe leaks and things like that. And also we transport a lot of fluids in and out of the well location. So accidents also pose significant risk to spills and potential contamination of groundwater, mostly near surface. So now let's move on to the completion phase of drilling a well. So there are, we'll just talk about the two kind of end members of well types. There's conventional wells, and then there are unconventional wells. Those are the big shale frac wells that you hear about in the news. So first we'll talk about conventional. They're actually fairly simple. Once you've drilled and cased the well, you move the rig out and a completion rig is moved in. Then there's still drilling mud that's inside the well bore. That needs to be displaced by completion fluid because the drilling mud will plug up the formation when you open it up to the casing. So perforation guns are then used. They're run in the hole and they shoot holes in the casing to establish communication between the casing and the formation. And then if necessary, sometimes we have small acid washes that are performed if there's damage to the formation from the drilling fluids and or the completion fluids. What the way this works is they pump maybe 500 barrels of acid down the hole and force it out into the formation. It dissolves some of the minerals that have plugged up the formation. And then when we go into flowback, that acid is produced back up out of the hole. Once the completion is ready, then we put hardware in the well that is designed to help get the hydrocarbons to the surface. That's when we start the well and flowback testing. Now let's talk about the unconventional phase. This is where we may have many frac stages performed on a single well. So the very first and most important thing to do when you're starting completion on an unconventional well is you've got to get your water. A large frac in a shale well could use as much as 2 to 16 million gallons of water. That's a huge amount of water. And so it takes time to get that in place for the operation, which might last over about 7 days. Once the water is taken care of, then we move a completion rig in, just like we did with the conventional well. Next, again, you have to displace the drilling mud that's in the well and use a clear completion fluid so we don't plug things up. Then the difference again here for unconventional is you've got a whole frac fleet of trucks and equipment and materials that need to be transported to the site. Then the frac is executed and then flowback and testing is done. Let's go to this next slide is about water storage, because I said water is very important. Here's first picture is an impoundment that's being built to hold water for the frac job. So they've bulldozed out a gully and they're laying down a liner, polyester liner, and that liner can be there for two reasons. One would be that if you buy fresh water and fill an impoundment up, you don't want it to leak out into the ground, or you'll have to buy a lot more water. Another reason why you might line the impoundment is that if you're recycling frac water from other wells, that recycled water will have some contaminants in it, and you don't want it to go down into the ground at the base of the pit and contaminate groundwater. So we've built the impoundment, we've filled it up. Now we're getting ready to start the frac operation. So this last picture shows a storage tank being offloaded at a frac site. What we do is we bring enough frac tanks in, or storage tanks in, for water for one stage. So when you begin a new stage, you pump water from the impoundment into all the tanks on the well pad. And then from the storage tanks, then you pump that down the well. Here's a picture of kind of a standard frac fleet setup on a well site. And the important things that we'll look at, we have water storage tanks. That's these over here. We have a chemical storage truck. There's much less volume related to chemicals, but they're important nonetheless. We have frac sand trucks. We have a sand conveyor. And these materials are all moved over into a blender, which mixes them up and prepares them to be pumped down the wellhead. Here's the wellhead here. So I'm going to show you a quick, because a multi-stage frac is a little bit complicated. I'm going to show a little video of a multi-stage frac job.
The first step in completing a well is the creation of a connection between the final casing and the reservoir rock. This consists of lowering a specialized tool called a perforating gun, which is equipped with shaped explosive charges, down to the rock layer containing oil or natural gas. This perforating gun is then fired, which creates holes through the casing, cement, and into the target rock. These perforating holes connect the reservoir and the wellbore. Since these perforations are only a few inches long and are performed more than a mile underground, the entire process is imperceptible on the surface. The perforation gun is then removed in preparation for the next step, hydraulic fracturing. The process consists of pumping a mixture of mostly water and sand, plus a few chemicals, under controlled conditions into deep underground reservoir formations. The chemicals are generally for lubrication, to keep bacteria from forming, and help carry the sand. These chemicals typically range in concentrations from 0.1 to 0.5% by volume and help to improve the performance of the stimulation. This stimulation fluid is sent to trucks that pump the fluid into the wellbore and out through the perforations that were noted earlier. This process creates fractures in the oil and gas reservoir rock. The sand in the frac fluid remains in these fractures in the rock and keeps them open when the pump pressure is relieved. This allows the previously trapped oil or natural gas to flow to the wellbore more easily. This initial stimulation segment is then isolated with a specially designed plug, and the perforating guns are used to perforate the next stage. This stage is then hydraulically fractured in the same manner. This process is repeated along the entire horizontal section of the well, which can extend several miles. Once the stimulation is complete, the isolation plugs are drilled out and production begins.
Okay, so that was as much as I wanted to show of that video. I hope it was helpful. That example was a horizontal well, which is somewhat different from vertical well multi-stage frac jobs. In a vertical well, you just start at the bottom of the well and you successively make later stages as you move up the hole. And typically in a vertical well that's being fracked, you use much less volumes of sand and water. So now we've completed our frac, and now we have our flowback operation. So the entire fleet, all that equipment that you saw in an earlier photo, that's all been moved out to a new job somewhere. And now we've brought in the few pieces of equipment that are required for flowback. So here's the wellhead over here. It has a pipe that it connects it to this separator over here. The separator separates the water, oil, and gas. The oil and water goes into storage tanks over here. These are just temporary tanks. And then the gas is either flared, or if there is a gathering line nearby, they might have connected it up to that gathering line. So Now we'll go through a summary of the risks during the completion phase for the operations of completion. So we'll talk primarily about the large scale frac operations because of the huge volumes of water. In some arid areas, this can put a significant demand on water resources and be in competition with irrigators and other people who need groundwater. That's a problem. Also, spills, of course, can occur during the operations. The good thing about the completion stage is it's a 24-hour operation and people are there all the time. And so if there is a spill or a leak, they are recognized quickly and remedied quickly. And again, as I mentioned on the earlier thing, transportation of equipment and materials is always a big risk with these operations. Okay, so now let's see about the production phase. So here's a schematic of a production setup on a well pad. In this case, we have two wells. They both feed into a pipe that goes to the separator. This is very similar to the flowback phase. You use a separator to separate the oil, water, and gas. Water can go either into storage tanks, or if there's a water treatment facility on the pad, it can go there. The oil goes into the oil storage tanks, and gas will be going into a gas gathering system, the pipeline. The oil and water, if it's in storage tanks, often has to be trucked out. So trucks will come in periodically and remove the fluid so that the tanks have room for more volumes to be put into them. Now, this next slide is the same thing. It's just shows a little bit better the secondary containment barriers that we use on above ground facilities at a well site. So the storage tanks have this retention barrier, the little square box that has sides on it. And every vessel that carries fluids has to have one of these. The wellhead is over here. And in this case now, the pipeline that runs to the separator is buried so that it can't be damaged and cause a leak. By EPA regulations, these retention barriers need to be able to hold 10% of the total storage capacity of the storage tanks that it's protecting. So now that we're producing, of course, the oil and gas is sent off and sold, but we do have produced water that we've got to deal with. And there are three disposal methods that I've listed here. One is evaporation in ponds. And then as the water evaporate, it precipitates out the total dissolved solids. And then those are removed and disposed of in a proper disposal facility. Another option is deep subsurface injection. And that's another way of getting rid of the water. And I had a talk earlier about deep injection and earthquakes, and I think maybe some of you have heard that. Last of all here, oftentimes the formations in Wyoming don't have very salty water. And so another option is treating the produced water. So removing the trace amounts of hydrocarbons, and then also using reverse osmosis to get rid of the total dissolved solids. And then the water can be disposed on the surface. That's a risky endeavor though, because the water treatment needs to be done very well. I'm showing an example of evaporation ponds because this is a common tool used in Wyoming. So here from the left, that pond is almost dry, and then they would remove the solids out of it and then fill it up again. And then as you go to the right, these are successively more full evaporation ponds. This is a map of Wyoming, and it shows symbols where there are commercial oil field waste disposal facilities. There are 33 in total. And again, most of these facilities use evaporation as a means of disposing of wastewater from oil field operations. There's another use for oil field wastewater. One is recycling for oil and gas operations. That's where you don't have to purify it too much, just enough to not interfere with the chemistry that you're trying to achieve with any operations that you're using the water for. The other 5 uses would require fairly good water treatment to make sure that we're not polluting things. So using the produced water for aquifer recharge, wetland development, livestock and wildlife ponds, irrigation, and dust control, that all would require high quality water treatment so that we don't pollute the ground surface. So summary of produced water. So you have a lot of storage, transportation, and handling, and each one of those steps often have risk of spills and leaks. And then water treatment and discharge requires really careful monitoring and hopefully a very ethical operator who wouldn't continue to discharge water if the water treatment plant wasn't functioning correctly. We have had some issues in Wyoming with situations like that. So that kind of completes the kind of a review of how drilling, completion, and production operations work. Now let's take a look at an example in Wyoming, which is Pavilion Field. Pavilion Field lies on a structural anticline in the western part of the Wind River Basin, which lies in the center of Wyoming pretty much. It produces gas, shallow gas, from the Eocene Wind River Formation and the Paleocene Fort Union Formation. I've put a red bar here in on the strat column to show the section that produces there. Also of note is that the Wind River is exposed at the surface at Pavilion Field, so it is also an aquifer, or a freshwater aquifer, in the uppermost portion of the Wind River Formation. Here's a histogram that over time shows the number of wells that were drilled in Pavilion Field. The left side y-axis is just number of wells per year. And then over on the right-hand side is a cumulative running average, or running total of wells that were drilled in Pavilion. So the blue line, of course, is just rising every time we drill more wells, and ends up at about 173 or so in 2007. Now, Pavilion Field, when it first was initially developed in 1960, had a well spacing of 1 well per square mile, or 640 acres. In the 1990s, the operators petitioned the Wyoming Oil and Gas Commission to reduce the spacing, and they were able to get that reduced to 40 acres. And that was based upon the fact that a single well couldn't drain all of the gas within an area of 1 square mile. Also, at the same time in the 90s, the operators began applying small-scale fracs in these wells. In the past, they had used acidizing treatments, but the frac treatments were a little bit better at getting through the formation damage, and they also increased a little bit the surface area that the reservoir had to flow into the well. Now, with all this activity, you can see there are a lot of wells drilled in 2001 and 2002, and suddenly we started getting complaints from landowners of water well problems. In 2007, that was the last year that any wells were drilled in Pavilion Field. And I'm not sure if that's because Encana was getting complaints from the landowners, and they were trying to not antagonize folks. But anyway, we have not had a new well drilled since 2007 in Pavilion. So with the complaints by the landowners, we went on a little bit of a journey at Pavilion Field. At first the EPA opened up an investigation in 2009. Then 2 years later, they published a draft document, and that document indicated that field operations and possibly hydraulic fracturing were involved with the water quality issues. At the same time that they released that document, they also asked for public comments and peer reviews of the document. And that's when things got really heated up. So there were industry folks that challenged the accuracy and the objectivity of the EPA document. And there was a big furor over this. So the EPA stepped back and they worked with Wyoming and Encana to come up with a plan for the state of Wyoming to conduct a separate study. And that study started in 2013. 3 years later, the Wyoming Department of Environmental Quality published their findings. They concluded that gas well operations could have impacted groundwater, but other factors may be the cause. And then they also said additional work needed to be done. So 3 years later, after additional work was done, the DEQ published a final report. Conclusions that they made were the same as what they suggested in 2016. They said it was impossible to directly link oil field operations to the water quality issues. So they also did say they wanted to continue monitoring so that if anything changed on the surface, we would be ready to make corrections to any problems that would arise. So now let's take a look. We'll go through the physical process used to develop gas resources in Pavilion and how they might have contributed to the water quality issues. This is a schematic of the type of depth deposits in the Wind River Formation and Fort Union Formation. So in the Pavilion area, we're out in the middle of the basin, more or less, or outward into the basin. So all the deposition is from in a fluvial environment. The sands tend to be discontinuous, not very laterally extensive. They do coalesce at times. A river cut will dig down into a previously deposited sand and then deposit sand on top of it. So there is actually communication sometimes laterally between these sand bodies. The formation is primarily sandstone, siltstone, and mudstone, and there is no real extensive seal or any highly competent sealing unit within either the Wind River or the Fort Union formations. In addition, because this is an anticline that was compressionally formed during the Laramide orogeny, we have natural fractures that have also created additional means of liquid transmission. Here are some pathways that could occur. We had vertical movement of natural gas, and it can go laterally within these sand bodies, and it can follow up these fractures. And what ended up happening was from source beds that are much deeper, we had vertical migration into this anticline, and the gas zones within the field are highly erratically distributed. And it just happens to be whether or not they have a local sealing mechanism that allows the gas to accumulate in the sand. Now, in addition to vertical migration of fluids upward in the system, by the way, I do need to say one thing. So there are a couple of wells, water wells that were drilled in the 1950s that found gas as shallow as 500 feet. So in the freshwater aquifer system, we actually had natural accumulations of gas. So in addition to the upward movement of fluids into the Wind River Formation, we also have precipitation, snow melt, and irrigation that percolates down through the ground surface and charges the unconfined aquifer of the Wind River that sits right up at the surface. And then in the 1960s, when gas started to be developed at Pavilion Field, we started poking holes in the ground. At Pavilion, you saw how a good well casing design is. In Pavilion Field, we have a surface casing that goes down to about 650 feet. And then we only have one other casing string, which is a production liner that goes to the TD, which is the deepest wells are generally around 55,500 feet at Pavilion Field. Now, the issue with this sort of setup is when you drill and set surface casing, generally we get good cement jobs on that surface casing. However, when we produce the liner, or when we cement the production liner in place, generally the cement will go down the pipe, come out and go up the annulus, and you'll have good cement for near the base for a while. And then as the cement slowly pumps up higher up in the annulus, it gets contaminated by bits of drilling mud and cuttings and things that are still stuck inside the annulus. Pretty soon you have poorer quality cement, which could provide leak off. And then also another thing that happens at Pavilion is the weight of the cement often is too much, and it creates a fracture out into the formation. And so the cement leaks off into the formation instead of going up into the surface casing. So there are a number of wells in Pavilion that are documented with cement bond logs that have no cement for a length of depth below the surface casing. And what that does is that creates an avenue for vertical migration of fluids in that annulus that doesn't have any cement. So here's one example. So say the well is producing from down here, but you've got a gas sand that's got poor cement where it intersects the well bore. Well, gas from that sand can migrate up the annulus and go into a shallower water sand. Now, this isn't going to be like a pipeline or anything like that. The gas will generally percolate. This will be a not a real high quality pathway for fluid migration, but we still can get gas contamination inside a freshwater aquifer via this annular vertical flow. So again, we're getting upward migration of materials, surface contaminants. We have cattle in the area. We have crop pesticides. We have unlined mud pits from wells drilled pre-1984, and we have septic systems. So our precipitation and irrigation is leaching these contaminants down into the surface, the unconfined aquifer at the surface. Those contaminants can percolate down, and as you go deeper, some of these sand bodies are not unconfined aquifers, they're semi-confined. So there's a lot of fluid capability for fluid movement. Although it slows down, movement can occur within these sand bodies. Here's a map that shows the domestic water wells. I call them domestic, it'd be irrigation and livestock watering as well. They're all shown in blue. And then the production wells from Pavilion Field are shown in red. And you can see that there are a lot of water wells that have gas wells drilled pretty close by. That, of course, is a potential cause of problems. So remember our casing design earlier. Here at Pavilion Field, we have surface casing and cement, but we're only down to 650 feet. And there are water wells in the Pavilion Field area that are drilled down to 900 feet. So we failed to set our surface casing at a depth to cover all the fresh water. Then on top of that, we have an open annulus because frequently we don't have cement that has been pumped all the way up into the surface casing. So we also have another source of potential contamination by upward movement of fluids. So take a step back. So Pavilion really is a field that's developed using conventional wells. Sands sometimes have low permeability, so the operators have started using small scale hydraulic fracturing to improve their productivity. Some of the completion depths range from 700 feet up within the freshwater aquifers and then all the way down to about 5,000 feet. I have to stress though, the frac jobs that are applied in Pavilion Field are very small and they're unlikely to have fluid movements that go very far unless this diagram has some fractures shown in the rock. If a frac stage is attempted to be completed and unknowingly at a position where there's a natural fracture, that can allow frac fluid to escape upward and screen out the frac stage. That's where you would get much more highly transmitted frac fluids. But again, with the volumes that they're pumping, it's not going to go too far. I have some data on frac stages, and the shallowest depth of a frac stage that I had data on was in this Pavilion Fee 4305 well at about 1,900 feet below ground level. The sand that they were completing in was 25 feet thick, and they pumped 18,000 pounds of sand and 4,200 gallons of slick water. And using just a generic calculation, that would have created a fracture that was 200 feet long in either direction from the well bore. So these are very tiny fracs. In an unconventional play, you're trying to get out maybe 500 to 1,000 feet if you can. So these are very tiny fracs. So let's summarize now what we've talked about at Pavilion and what are the potential sources of problems. By the state, the DEQ documents, they are contending that water contamination is complex and it's really difficult to diagnose the sources. You can guess, but they are correct. It's difficult to perfectly identify where something has come from. We did have gas in some shallow aquifers before the field even started to be developed, and that was due to natural migration. Our surface casing depth is definitely not adequate to protect groundwater resources. That's a surefire regulatory failure. That should not have ever happened. Next, we have cement for production casing. Should be pumped all the way to the surface, or at least up to the base of the surface casing. And we have multiple instances of that not happening. And it causes the ability to have fluid migration between different flow units. Hydraulic fracturing, which now is preferred in the field, should be limited to greater depths unless the operators can prove that the induced fractures are not a threat to fresh water. So real shallow gas sands should not be hydraulically fractured. Another and the primary reason why not to do that is because natural fractures in the Wind River make shallow frac stages risky because you just have uncontrolled fluid movement if you happen to intersect one of those natural fractures. finally, we'll get to the pits. Prior to the 1980s, unlined pits were used for drilling operations. They also commonly used oil-based mud because the mudstones, well, the shale within the sandstones is sensitive to water, and it swells, and so you had problems with drilling wells using water-based mud. But the pits that they used, the reserve pits, and were often unlined, so they had oil-based mud in an unlined pit, and then they also dumped the cuttings from that well into the pit. And frequently, as you saw in that picture I showed, that a lot of times they did not dispose of the cuttings, they just buried them in place. I do want to add, though, one thing. Since the 1990s, all those newer wells that were drilled in Pavilion Field, closed loop drilling systems were used for all of those wells, which is a good thing. We didn't have any more pits to worry about, just the old ones. So the operators were doing something good when they drilled those wells. Okay, with that, that's all I had to say for now. And thanks for listening. And I'm happy to take questions now.
All right, Dan. There were some questions. There may be some more, we'll see. But let me go ahead and pose a few to you here. One is, would you drink the well water from the Pavilion Field area?
From the what field area?
The Pavilion Field
Oh,
area?
Pavilion. No, I don't believe I would.
Okay. All right.
So I don't know whether they do any surface disposal or anything like that, but no, I would not.
Fair enough. You know, the information you provided about the studies of Pavilion Field were sort of contradictory. So is it fair to say that we maybe really don't know the answer to what causes problems in Pavilion Field, or is it just there's just ongoing arguments?
It's kind of both. It's hard to really get rock solid proof, you know, that fluids from the drilling and all that got into the water zones, the water wells of the residents there. I have a pretty strong opinion that based on having the surface casing not in the right place, a lot of open annuli in wells, I don't see why you wouldn't have an increase in contamination in those aquifers.
Okay. Another question is,
so the state of Wyoming was very evasive. They did state all of the points that I made about you know, possible sources of contamination, but they just wouldn't say that it happened.
okay, maybe a related question, and that is, you know, presuming that there are some quote unquote bad operators out there, how are they weeded out, or are they weeded out, at least in the state of Wyoming?
That's a good question. So let's take the case of Encana. They bought Tom Brown Incorporated, who was a Colorado operator, and they ended up with Pavilion Field. And when they went to try to increase production there, that's when they ran into all their trouble. They used, so the problem is with surface casing, generally when we're developing a field, we use the historical casing depths. And the problem is the state of Wyoming never set the casing depth correctly for the depths that people were drinking water from. And so I almost can't say that Encana is a bad operator. They did use closed loop mud systems. They tried to be responsive to the residents. You know, I guess I probably have to talk to some residents to find out a little bit more about, you know, how much they work to try to help them out. But I know there are certainly some operators that don't give a hoot, you know, and if they can save a buck, they'll do something that they really shouldn't do.
Okay, so I'll just follow up on that. Is the Department of Environmental Quality in the state of Wyoming doing the job that it should be?
It seems to be. They wouldn't actually come out and say anything about the oil field operations being the cause. So I think they are wiggling around on that one. But I think it would take a little bit more work. They do allow surface disposal of produced waters. And I'm not quite sure how rigorous the restrictions are on the quality of the water.
Okay, question about sort of fracturing, hydraulic fracturing, and that is, now how far from the well can fractures, the induced fractures actually extend? Can they escape the production zone? Can they even reach the surface?
They wouldn't be able to reach the surface. So I gave that example of the 200 feet of frac length growth in the zone that's at about 1900 feet. If the fracture breaks upward out of the zone, you still only have a certain volume of fluid that you're pumping. So if it grows upward, that's at the expense of the length of the fracture. So you just change the orientation. So, you know, if it were 25 feet wide next to the wellbore, then it only went 200 feet up.
Okay, there was a question about, the mud pits, the various fluid ponds that are associated with drilling. And, there was an example a few years ago of waterfowl, landing in these and dying, I think. And so the question is are operators required to protect waterfowl wildlife from these pits? In other words, is netting required?
There are some requirements to that, but I believe it's when they're more permanent. So this is a problem with our state requirements, because if you drill a well and you have a frac pit that just held fresh water, you don't have to. You have 1 year to rehabilitate that pond, and so I'm not sure, but it may be possible that you don't have to put netting over a frac pit, or that is not that's going to be reclaimed.
Okay.
Any operation that has a permanent pond has to have netting over it.
How long can a well, a drilling and well development process or operation extend that? How long can that be underway?
I'm not quite sure I understand that question. So,
well, if you're worried about the waterfowl, for instance, what's the time window for which they could be at risk?
Oh, as long as there's water in the contaminants in the pit.
Months?
The operator has 1 year to close the pit. Okay.
Is there always salt water beneath the freshwater zones?
Not always. I actually wanted to talk about Moneta Divide Field today, but I found I didn't have enough time. And that's an instance where at 15,000 feet, Encana had drilled a water disposal well. They had hoped to dispose of water in the Madison Formation, and they found found out that the water was fresh, and so they weren't allowed to dispose into the Madison because of that.
Okay. Question about the acid that is used in at least some of the hydraulic fracturing procedures. What happens to it? Because if the question is, if I understand correctly, those fluids do come back to the surface.
Yeah, acid that's generally used is to open up perforations, and it gets spent pretty quickly, and it isn't a large volume. And then the frac would be pumped. And so some of that acid, spent acid, would remain in the ground, and then the rest of it would be produced out with the flowback water.
Okay.
And then hopefully properly disposed of.
There was a question about the drilling procedure itself and the cuttings. Are they used for anything, or is it just to clear the hole?
The cuttings are it's just important to clear the hole, otherwise the drill bit would get stuck. There are, I did see some discussions about actually washing the cuttings and using them for other things. So sort of like recycling the cuttings themselves. It would kind of depend on the type of drilling mud that was used. If an oil-based mud was used, you probably wouldn't want to do that. But I guess they do retort them and can burn off hydrocarbons. I just saw a brief mention about that. I didn't do any research on it.
Okay. How are drill sites selected?
There are a lot of tools that we use. Generally, in a major field development, you'd have 3D seismic data, and you'd be using that data to map your targets and select locations. And wells that you've already drilled, you use that experience of how well they performed to select other locations.
Okay. Question about what is frac sand? Is it just river sand, or what is it?
There are many types. The lowest cost sand is just river sand, and it may be a brown sand. Up north in Ohio and Minnesota, there are a lot of sand farms. Basically, it's just fluvial sand that they mine and sell to the industry. There's also bauxite, which is used. And then also sometimes if you have a sand that isn't strong enough to hold the fracture closure pressure, sometimes they put a resin coating on the sand, and it increases its strength. And then if you need even more strength, that's when you use bauxite.
Okay, there was questions come in saying that they believe they've heard that radioactive fluids are used in fracturing, hydraulic fracking. If so, why?
I'm not aware of any. There's no real reason to use radioactive materials. Sometimes we put a tracer if you're trying to figure out where the sand is going in a vertical well. Sometimes you'll put a tracer in there, but it's not really a hazardous substance, and it's only at the very end of the stage. It's at the sand that's right near the well bore.
Okay. Question about how much wells cost to drill and produce.
Well, there's a wide range, of course. Let's say a 10,000 foot vertical well would probably cost about $2 million now, if it's not a real huge fractured, unconventional well. And then a very large, long, horizontal conventional well can cost, up to $10 million, maybe 12. Might be more now. I haven't been working in a while, so.
And of course, as you and I both know, a well in the offshore in the deep Gulf of Mexico could cost $100 million.
Yeah, or 250 is on a project I was working.
Okay, and this may be the last question here. Does the water for drilling, hydraulic fracturing have to be fresh water?
No, it does not. And that's a very disappointing thing for me, because we should be recycling frac water and using them for other fracture jobs. We had a situation in the Permian Basin where we had brackish water. We had a water well that we drilled to source our fracturing jobs. And the landowners would get on our case and they would say, well, you can't drill that well there because you're not buying my water. So they would insist that we buy his fresh water so that he could make some money. And we wasted fresh water on a frac job that didn't need that fresh water.
All right.
It was very frustrating.
Yeah, no, there's a lot to all of this. Yeah, I mean, this is a topic you could talk for hours on, literally. I'm sure we've lost everybody long since, but there's a lot to it. That's the list of questions. So thanks for addressing those. Thanks for, a very interesting, well put together talk. And let me just remind everybody before we close this out that in 2 weeks' time, Angela Reddick from the Wyoming Dinosaur Center over in Thermopolis will be here both on Zoom and at St. John's Episcopal Church in Hanson Hall. So you can participate in that program either live in person or via Zoom. And she's going to talk about sort of a pre-Tyrannosaurus Rex dinosaur, Allosaurus, that ran around for a long time, and it was every bit as big, or at least pretty nearly as a T-Rex, and an excavation site down in Utah, and what they have found there. So that should be very, very interesting. So many thanks for that again, Dan.
My
I
pleasure.
much appreciate it. There are a lot of good questions, and it was fun to listen and watch, and appreciate all the work that you put into this, which I know was a whole lot. It always is. So
Yeah, my heart goes out to the people in Pavilion.
yeah, I mean, aside from possible petroleum product pollution, as you well pointed out, that freshwater system there with all the chemicals that people put on the surface there for agricultural purposes would keep me from drinking the water there, aside from the oil and the gas, I think, and other pollutants that might have gotten in from various wells. Not an ideal situation.
No, very complicated.
All right. Thanks. Thanks to everybody. And we will hope to see you. There's a good program again in 2 weeks then. So good night, everybody.